Next in the agenda, we have Professor Christine Rousselle. She is a professor at the University of Orléans and has been working on ammonia a lot. So and that's one of the main reasons, because she's leader of combustion studies on the fuel, mainly for application in internal combustion engines by means of metal, optical engines, high temperature, high pressure vessels, etc. So Professor Rousselle, the floor is yours.
Thank you, Agustin. Good afternoon, everybody. I would want, during this presentation, to try to do a kind of state of art and about future challenge in order to consider ammonia in engines, especially by considering what we know. So first, I want to start with a small joke. The first people who consider ammonia engine was the French engineer in the 19th century. But as you can see, it was not really ammonia as fuel, but it was a steam engine. Anyway, Dr. Room already showed this morning that from the past, there are different examples of the use of ammonia as fuel for vehicles, but we can see that since the last year, so recently, there are new projects like, like the hydrofuel project in Ontario University. The objective is to develop trucks full with ammonia with hydrogen or hydrogen. Also, there is the C3 Run project in Iowa University. And what it is interesting, it's in fact start and stop of the engine is done by using hydrogen. And when the engine is sufficiently warm up, in fact, they can run with 90% of ammonia and about 10% of hydrogen. And more recently, there is a new project, Activate, from the Norwegian government. And the objective is to develop a small tractor for agriculture vehicles. Sorry. Okay, but as most of you know, tomorrow, if we go to the website, we have a lot of advertisement about what could be, in fact, some kind of mobility with ammonia, especially for marine application. Even if they have this kind of advertisement, I'm not sure that until now there is any ship that can run easily with ammonia. Okay, why ammonia is so relevant to use as fuel for internal combustion engine? Sure, it's great because there is no carbon content, so there is a zero carbon footprint that we can achieve, but also no CO or not particulate matter emissions. We not exactly know because we can have some issue about lubricants. There is a good energy density in comparison to hydrogen itself, and it is more similar to gasoline or diesel fuel. But what's about ammonia combustion characteristic? I don't want to take so many time to explain again, as we already see a lot of presentation on this purpose during this day. But if we compare only auto-ignition delay in comparison with methane, hydrogen, sure, but methane or isooctane on even methanol, we can see that the auto-ignition delay is very important in comparison of this fuel. Also, the adiabatic flame temperature will be strongly lower, less than 200 Kelvin lower, and the laminar flame speed is so small that we can have some questions about the good way to use ammonia in engine. And also what it is also interesting, it's the extension strain rate is very small. So higher ignition delay, lower adiabatic temperature, lower laminar burning speed, lower extension strain rate. Can we think that it is possible to run in engine? Certainly, it could be possible if we use higher compression ratio that we can use currently. Do we need a combustion promoter to boost performance, ensure stability? But what we can know, it's in fact, as ammonia, it's a fuel-bound nitrogen, we will have NOx emission and also N2O. And most of the time, we forget that we can have unburnt ammonia and hydrogen. Even if we use only ammonia as fuel, at the exhaust, we can have some hydrogen, which, due to the decomposition of ammonia in situ in the combustion chamber itself. So it's clear that we need some mitigation strategy to limitate pollutants and also to develop accurate, in fact, post-treatment, as we will see after my talk. And as you know, unfortunately, ammonia is corrosive and toxic. So internal combustion engine fuel with ammonia remains very challenging. What do we know exactly? From the past, from the different studies that we can have, in fact, as any fuel, we can consider spark ignition engine or compression ignition engine. To boost the combustion, we need ignition or combustion promoter. Also, in a compression ignition engine, we need at least a compression ratio until 35 in order to auto-ignite ammonia. So we need the help of reactive fuel to promote the ignition. From the past, there are different B-fuel experiments, blends, with gasoline, natural gas, methane, alcohol, hydrogen, or for compression ignition engine with diesel, biodiesel, DME, and hydrogen. When we decrease the content and when we go until hydrogen and pure ammonia, it's sure that we will decrease also the carbon footprint. Therefore, to try to use ammonia alone in internal combustion engine, we build the best choice to reach the zero carbon footprint objective. Some recent examples that we can see from the literature about a spark ignition engine. So it's the last 10 years. First, from Pisa University, they use a very small engine with a port fuel injector, and it was with ammonia plus hydrogen. And also they study the opportunity to use, in fact, this kind of engine like a range extender. More recently, we have another interesting study about the possibility to mix gasoline and ethanol on ammonia, but we can see that the content of ammonia remains very small. What it is interesting is the idea to develop an emulsion between ethanol, gasoline, and ammonia. After, in Orléans, we study pure ammonia or ammonia with hydrogen. It was in a current single-cylinder engine, fully premixed on regular compression ratio for spark ignition engine. More recently, we have a new study between natural gas and ammonia blend with the unique study that it was in heavy duty. And it was injecting in premixed port fuel injection with a relatively low compression ratio engine. And recently, there is a new result from Toyota Group, and they especially focus on the cold start in order to reform a little bit ammonia and to ensure, in fact, the start of the engine. The compression ratio was relatively low. About compression ignition engine, The study showed different application. Most, we can see that you have dual fuel, on dual fuel, on dual fuel. And what we can see, it could be with DME, it could be with diesel, or if diesel. But it is important to note that, in fact, it is no more than 40% of ammonia in fuel. And what we can see, we have only one study about to consider, in fact, HCCI combustion with ammonia. And also what it is interesting is to note this last study with its bigger engine with a high compression ratio. Okay, if we summarize a little bit what we can know from this previous study, in fact, in the case of compression ignition engine, in comparison to diesel full engine, the addition of ammonia increase the torque significantly, decrease hydrocarbons on CO2 emission, but can decrease also NOx when ammonia content is higher than 70%. When it's blended with DME, in fact, we can see that the maximum NG load is relatively limited. We cannot reach the similar value that we can have with poor DME. And also that we have hydrocarbon on CO and NOx increase, but a strong decrease of soot. If we look on the spark ignition engine, in fact, we can compare with hydrogen full engine, natural gas, or gasoline. What it is interesting, it's in fact with hydrogen, we increase the cycle thermal efficiency on the NG power, ensure we have no carbon emissions and same NOx emission that we can have with gasoline engine. With natural gas, in fact, you have a peak pressure decrease, but unfortunately, we have a NOx on NH3 increase. So if I did last week research about what are the more recent studies that we can have in 2021 and 2022. In fact, more than 8 review papers and more than 12 research papers about to consider ammonia as fuel in engine. It's clear that it is a lot of new interest, but what we can see also that there is a lot of paper based on the simulation in order to have an idea what could be the advantage to use, in fact, ammonia as a fuel in engine. Can we simulate ammonia engine with high accuracy and predict ammonia combustion in engine? In fact, we have different possibilities to use ammonia only in internal combustion engine. As I already told you, it's difficult to auto-ignite ammonia, so we need an igniter, spark one, or ignition by pilot fuels. Ammonia can be provided in the engine in gaseous phase or liquid phase from port fuel injection, direct injection, or perhaps both. If we consider that we want to add hydrogen as ignition promoter, we can consider to have another tank with hydrogen or onboard reformer. This will be, in fact, it's a spark ignition engine. And what we have to deal with, it's to optimize the load as function of the engine speed, to resolve the problem of cold start of the engine, and also to reach, in fact, a kind of ammonia NOx emission trade-off. If we use a pilot injection of a reactive fuel, we can also use a diesel design engine and to optimize, in fact, the different injection system. As everybody knows here, if we consider what I can say a dual fuel engine, but it is not really dual fuel engine, it's kind of RCCI engine, because the idea is really to add a small quantity of reactive pilot fuel spray or classical spark ignition engine. For both, we have a lot of fundamental characteristics that we have to better understand before to be sure that we can predict the combustion development in this engine. For the first time, we perform, in fact, some visualization of ammonia flame propagation in internal combustion engine. It was with NH3 ignited by decane pilot injection. It's less than 11% in energy input. And in comparison with spark ignition, in the same engine but without decane, we have in fact a spark plug. Yes, so this is a classical premix flame. Even it is a diesel architecture engine, we can see that the flame is really premix flame propagation. And here we have first the ignition of a decane pilot quantity, and after straight away we have the development of the premix flame. Okay, so as I already told you, we have different ways to consider the injection of ammonia. For vapor fuel, we have a problem of displacement of the air supply to the combustion chamber, the reduction of the volumetric efficiency of the engine. If we consider direct vapor fuel injection, we have a we'll have a reduction of in-cylinder temperature due to ammonia highlighted of it. And if we consider liquid ammonia injection, we will have better volumetric efficiency, but it's clear that we have a strong decrease of temperature in the combustion chamber. The problem is, in fact, about ammonia injection, we know nothing. There is only 2 studies focused on liquid injection. And if we look on the vapor pressure trace, it's very different than what we can have with classical fuel like gasoline or ethanol. And if we look at the spray development, it's clear that due to the specificity, in fact, we have a narrow spray and certainly inside with plenty of vapor contents. So what's the consequence of the flash balling specificity? How can we consider that vaporization models are accurate? There is another study more recently. It's a very interesting study because, in fact, they study injection of ammonia with also injection of diesel pilot fuel in a rapid compression machine. The injection pressure was relatively high, around 500 bar, but this work is in process. So for the moment, there is no image on the ammonia spray characteristic. About gaseous injection, there is a recent study when we can observe, as function over time, the penetration of the gaseous jet. And we can see that, in fact, we have a different phase of the development, but it is not really well known because it's more like a diesel spray. But what it is interesting is when they compare with methane, it's quite similar. So perhaps it could be possible to substitute ammonia with methane for modeling purpose. But we have to consider sure that there is a big difference on local equivalence ratio due to the air-fuel ratio for ammonia. Okay, how ammonia can be suitable for lower engine speed due to its low flame speed? It will be really limited by narrow flammability limit and also the low flame speed itself. Do we reach incomplete combustion? Do we reach misfire? What about ignition process due to intrinsic flame instability? And one possible way to enhance mixing or thereby facilitate combustion of ammonia, do we need to increase the turbulence in the combustion chamber or not? As we already see today, there is not so many data about ignition delay, especially when we want to consider ammonia ignited by a diesel type pilot injection. We have recently some data about NH3 with NF10 or NH3 with DME with a small quantity. But this is relatively new, and we have no data for many temperature values. For example, if we consider again the problematic of ignition by another fuel, there is only one study about the impact of ammonia on NF10 ignition delay. And what it is really interesting, in fact, the addition of ammonia in NF10 change, in fact, the ignition processes and greatly dealing the first state ignition. Also, about the laminar flame speed, there is no so many data about laminar flame speed evolution with regular fuel like here NF10 or isooctane. And here it's also for ethanol. It's a recent study when we try also to see what will be the effect of the content of ethanol in ammonia flame. Okay, about premixed turbulent flame interaction. Also, there are some studies about premixed turbulent flame interaction. Most of them are focused for gas turbine application. And there is only one about what could happen, or what kind of combustion turbulent regime that we can have in engine. And what we can conclude, it is not really easy to correlate with the Lewis number, especially when we have some ammonia hydrogen blend. Karlovitz is not sufficient to predict, in fact, turbulent flame speed for high ammonia content. The mix between Denkoller and Karlovitz is better, but it's clear that it's a complex diffusion thermal instabilities and turbulent interaction. Before to finish, I want to focus a little bit on cold start problem that we have to deal with before to consider seriously ammonia in engine. So, in fact, we know there is a low flame speed on narrow flammable limits of ammonia. This will conduce to combustion instabilities. Moreover, low combustion efficiency, especially at low load, we will have more unburned NH3. Recently, in a Toyota paper, in fact, they highlight that only Frigo et al., so it was in 2013, investigated the cold start of a two-cylinder engine burning ammonia with an external hydrogen supply, and their conclusion that it needs a lot of hydrogen, about 5 times larger than that of NH3, to start, in fact, the engine. The consequence will be that we need another hydrogen tank to start the engine. But in this study, in fact, they try to start the engine by considering, in fact, thermal reformer, so onboard fuel reformer. And what we can see, it's after 30 seconds, in fact, they can reach sufficient stable IMP and only run with fuel ammonia. Okay. Perhaps we can also increase the compression ratio in order to avoid to add 300% of hydrogen at the start. For that, we try to see what's happened in a classical spark ignition engine versus a spark igniting diesel type engine. Why? Because diesel type engine is designed to run at high compression ratio. So moreover, we can retrofit current diesel engine, it will be less expensive. Okay, but the main problem with this type of engine, there is no turbulence, only strong swirl motion. And also, due to the classic ball shape, we can have a big squish zone. It means that we can certainly have more unburned ammonia. So this is a two view to explain the difference of two kinds of engine architecture. So here we plot what we get in a spark ignition engine with a compression ratio of 10.5. This is as function of the equivalence ratio, not so far from the stoichiometric one. So lean case, rich one, stoichiometric. And here it's with 0% of hydrogen. And we try to see what will be the minimum of IAP that we can reach with this kind of engine full with ammonia. And we can see that we can reach only 5 bar of IMP. So it's very high. It's not start conditions of the engine. And when we add in 5% of 10% of hydrogen, we can reach lower than 3 bar. If we compare with the diesel architecture, we can see that, sure, as expected, when we increase, in fact, the compression ratio, we can decrease the IMP limit. And also what it is interesting, we don't need hydrogen. Also, we did also the same with at lower engine speed, and it's clear that we can reach the same minimum IMP that obtained a Toyota group with a reformer. Oh, sorry. Okay, we continue this study by in fact test different type of engine architecture on the different type of piston ball. So here it was our current spark ignition engine, and we use another spark ignition engine when we can in fact change the compression ratio, but we can see that when we change the compression ratio, we change also the piston shape. So it means that in fact we change the turbulent flow field. We will increase with this the turbulence near the top dead center. This it was I present before. It's our diesel engine type architecture. The spark plug was not centered, but it was a little bit in one side. And so this work is done in ARENA project. It's an European project when we try to see what we can do with ammonia as fuel. This is done with Stellantis, so Peugeot group for us. And we do also some other test with Aramco and Stellantis in order to try to optimize, in fact, the ball shape in a diesel type architecture. And what we can see first, we use a centered spark plug, and here we improve the ball shape. Here we plot the minimum IMP that we can reach by ensure sufficient stability. And this is the first result that we can have. So first, when we have a spark ignition engine without hydrogen, we can improve, in fact, this limitation by increase the compression ratio. But it's not so easy to say that, okay, we obtain straight away a better limit, because you can see, for example, here, even if I increase the compression ratio from 10.5 to 11.5, so this point to this point, in fact, what's happened? The IMP limit increase. This is due that, in fact, the turbulent flow field was different. Here, it's when we increase the quantity of hydrogen, it's sure we can reach very low limit. Here, it's the same compression ratio in spark ignition engine, and here in diesel type engine, we can see that we can reach really different limits, even if the compression ratio is different. Here we have high turbulent kinetics energy. Here we have no turbulent kinetics energy. And we increase the compression ratio from 14 to 16. So we continue to decrease, in fact, the IMP limit. But when we try different engine architecture, so it means here the spark plug is centered, and here we try another pole shape, we can see that it is not so easy to, in fact, provide some conclusion. In fact, if we look at spark ignition to compare with spark ignition diesel engine, here it's what we have as laminar flame speed at the spark ignition timing. Here with ammonia only. And also the consequence of the laminar flame speed, it's clear that in fact we cannot reach the same value that we can have with by adding some hydrogen content. So it's not really due to the increase of the compression ratio that will enhance the laminar flame speed value. It's more complex than that. In fact, spark ignition engine in a turbulent combustion diagram, it's somewhere here, our current engine. And when we use, in fact, high compression ratio engine in diesel engine architecture, we go here due to the fact that the turbulent kinetic energy doesn't exist. And in this case, we are again in the thin reaction zone. When we try to increase the spark ignition engine with high compression ratio, we can be here or here, it depends. As you can see with the compression ratio of 11.5, it was worst. So in fact, also there is some other important things that we have to deal with. What is the sensitivity of ammonia or ammonia plus hydrogen to the stretch? This will, in fact, increase the flame instabilities in the engine itself. So it is not so easy to answer to the question, what flow field optimization, one engine design for ammonia combustion? Last, if we compare all these engines and at the spark ignition timing, I compare the laminar flame speed, we can see that in fact the value could be so different, but at the end, so this it's at pressure, intake pressure of 1 bar. It's not a limit IMP. We can have similar, in fact, IMP, but we can see that without hydrogen at the compression ratio of 10, the laminar flame speed is not high, but in fact, we can have similar IMP that we can have with 10% of hydrogen. So really, it's very difficult to conclude what will be the best engine for tomorrow. The consequences on exhaust emission are also very important. Here there's all of our engine. So it's for the intake pressure of 1 bar, what I just show you, in fact, the laminar flame speed or stoichiometric air fuel ratio. Here it's the standard spark ignition engine. We have about 1000 NOx emission in ppm. But when we increase, in fact, the compression ratio, we can see that we have highest quantity of NOx. And in the overhead, with the diesel architecture, the quantity is very low. But when we increase again the compression ratio, we reach higher quantity of NOx. What it is important also with N2O, many people ask, what's about N2O emission? What's about N2O emissions? We can see that for all cases, we have lower than 45 ppm of N2O, but this can represent 0.7% of CO2 at the exhaust, so it's not nothing. Moreover, we have another problem. It's NH3 emissions. And sure, diesel and architecture engines seems to be very indicated for premix combustion with ammonia. But we can see that the main drawback will be that we will have a lot of NH3 at the exhaust due to the trapped in interstices like the squeeze zone on some crevices. Okay, so what are the challenges still now for ammonia fuel in internal combustion engine? We saw that there is a technical impact of the injection system, ignition range, cold start, compression ratio, boosted conditions, combustion stability, operating conditions range, efficiency, thermodynamic conditions, and also about exhaust pollutant emissions. And we still need a lot of fundamental study in order to provide accurate, predictive CFD modeling. Thank you.
Thank you very much, Christine, for that very nice presentation.